Hey, welcome back. We're coming back to solving these differential equations and the Perkistocone problem. Last time I was taking a look at trying to, and I'm double checking that our stream is up and running. Let's make sure this problem. Last time I was taking, mute that. So I was taking, should be good to go. Reconnecting. All right, so it's reconnecting. I thought I was just up and running, right? Felt like it was going. Stay here. Oh wait, I see. Close that one. Okay, so solving differential equations for this Perkistocone problem. I was running into some issues, partly because with this Perkistocone, here, let's pull up Perkistocone curve, and there are some cool ideas in the chat as we were kind of talking about stuff. Let's see, in here, let's go over to GitHub. In our discussions, this so Vsauce had a nice video about it, and then another one was the finding the solution to this Perkistocone. So what I was doing in Julia was looking for a numerical solution, but part of the problem is it gets hard to find solutions when you have like a slope that goes to infinity, kind of like this. And so the true solution that we're looking for is kind of like a 90-degree drop into a slowly varying curve. So here's like a circle versus that cycloid. So it becomes like a sharp point and then comes back down. And I was running into all sorts of like numerical errors along the way. Let me see. Anything else useful in here? So this is kind of tracing out like the path of a point on a rolling ball. But anyway, so create this differential equation. Let's zoom in a little bit. And main thing that I wanted to show last time was like if you know what the differential equation is, and let's put a new, or actually, yeah, we'll put it in here. So my differential equation is f double prime, or yeah, we'll call it f double prime equals frac of 1 plus f prime to the second over 2f. Oh, it would help if I put that inside MD 1, 2, 3, and then 1, 2, 3. Okay, and I'll hide that. So this is my differential equation, and what I'm doing here is splitting that up into two differential equations. So since it's a second order thing, here I'm setting it up as like the derivative of f is df dx, and then derivative of f prime is my differential equation here. And if I set up some initial conditions for it, so what is the initial position at 0? What is the initial velocity at 0? Or sorry, not velocity. What's the initial slope at 0? Then I can say from 0 to 1, show me what the answer to this cycloid is. And so I get an answer. So I plug it into, I create this thing in the ODE problem. So if we look at like live docs, it's specifying like, okay, I have a differential equation. It's assuming that it's a function of time, but time and space, it's all interchangeable. It's just like math things. We can sub out x versus t. And then this solver in here is just coming down here. We can specify like the relative tolerance, absolute tolerance. I don't know why I'm specifying both. I had grabbed this from an example. The fact that I have both of them, I think one is kind of overriding the other. But anyway. And then the final part is just like, okay, so show me t and f. So this is my f of x and this is my x parameter. What I can see here is like I'm not getting all the way to 1. I'm like a little bit, I'm close but not quite there. And if I add another thing here and look at sol t, let's go end minus 10 to end. I'm getting the same, I'm solving the same thing over and over. Like I'm not quite getting, I told it to get to 1, but it's like 0.98, and it keeps giving me lots of answers there because this slope is getting so, it keeps growing. Really, it's not that big of a deal, but I had to play around with this because I can't just solve, I couldn't solve it. I was running into numerical errors. Yeah, it's just the nature of using computer to solve problems. It can be very accurate, it can save time, but it can also introduce new problems that you don't really think about when you're solving it by hand. But the nice part is it's always the same approach. Set up an ODE problem. So by defining your, at least the way that I think of it is like define your function, like what are your derivatives, and then give it the span, the time span, and the initial condition, and then your solver is going to step through each of those solutions. And we can delete this one now. And what I tried to do was set up, so I started here, I'm starting at -1, so at 0 I'm -1, because this whole thing was kind of flipped. It was hard to get this thing, because if I say this was 1, then I end up with like this upside down kind of curve. So what I wanted to do was flip the whole thing. So I said, all right, start at -1. So as if I'm starting up here and rolling down to -1. And if I just add 1 plus that, now it's starting at 1 and going down to 0. So it's basically it's doing what I wanted it to. It was just giving me a little bit of trouble along the way. Okay, so that's how I started. And then my thought was, oh, I have a shooting method problem where I'm trying to specify like, hey, I want it to be this given value at the end for this initial slope. But because this is kind of a weird nonlinear, it's not like a super weird, it's a problem that has been solved many times, but it's a nonlinear kind of problem. The shooting method that I define, where I say, show me what the solution at the end is, and if it's 0, then it's true. Remember, I'm starting down here. I'm starting at -1 and going up to 0, and my goal is just grab this curve, flip it around, and then see how long it takes to get down it. So my input is that derivative at f0. What I found was it kind of it goes to 0, but it's just, it doesn't change. So there's no sign change. It never becomes like a positive because it's describing a cycloid, which is this problem of like like this point V being tracked as it moves down. So it's never going to go above 1. Like this thing can't roll. It's not rolling like up a hill or anything. And again, I'm just kind of talking through like what were the issues that I was finding, and hopefully that helps you as you're kind of thinking. Main thing here is like there wasn't anything wrong with like the Julia programming. Like I had the right arguments. They were all in the right order. Everything was doing what it was supposed to. It was just I didn't have the right I wasn't using my own engineering intuition to actually interpret like why is it acting this way. So because of that, I figured out like, okay, I have to be at least 3.85 or 3.82, something in there. And if I use like 0.4 or this 0.385, oh, too many zeros. This is again, I'm flipping the direction, so I'm starting at 0 and going over to 1. This is what the shape of that curve looks like. And now I can plug it into that time function from coming back here. Same thing here. I have a new path defined that's called the brachistochrone, like that path. I can figure out what is the total time to the bottom because I have all the points in here. So I'm using the same function. It's a little different this time because I'm using finite values. I don't have an actual function, so I can't say f of x. I have to just grab the actual values f and df, which I get from my numerical integration. And we can compare that to all of these parabolas that I created. And coming down here. So kind of building all those different parabolas in the same way versus this brachistochrone kind of ideal solution in bold orange. And we can see like roughly this one that was the fastest. It's pretty close to what this curve is too. It's off by a little bit, and that's okay. Like we're trying to get a sense of like using numerical methods to do like math here. To help us like explore, I guess is the main thing. So it's helping us explore it. If you see a way to like fix any of these issues, like definitely feel free to jump in and offer a solution. But this is what I got so far, and it seems to be working. It's doing at least what I wanted. And so I took all those different parabolas, plugged them in, and so there's y1 through y15, all these different ways of getting down this curve down to that point of 0. And if I compare that to the time that it took to follow this orange path, I can see it was 0.25 seconds or something, versus even the fastest parabola was half a second. And that's what I'm doing here. It's like calculating what is that total time, what's the total time using that brachistochrone solution. And integrating area under that curve. Total time there. And that's it. So much faster and better. Better, like a faster curve. So this curve is much faster than any other parabola. Definitely faster than this. One of these is the straight line, like the shortest path, right? Cool. And like, yeah, if you're like me, you might think like, well, how do we know that this is the fastest? Right now, what we know from this is that this is the fastest smooth curve, that if you have a continuously differentiable function, this would be the fastest way to get there. And if you think that discrete, like having things that are non-differentiable are faster, then we would need a different method of like trying to get to that optimum solution. But the way that we got here was with those variational calculus, using some variational calculus and getting there this way. All right, so how does this connect back to, like, what's the next step here as we're thinking about like dynamics and these kind of things? Well, in dynamics, usually we end up also with second order differential equations. Sometimes they're linear, sometimes they're nonlinear, but it's the same process where if we want to define a function, then we need some way of figuring out like how do we evaluate and kind of analyze what that function is. So what we can start with is kind of this harmonic oscillator. So this one, hopefully you've seen like these solutions before. Harmonic, do we want to use that? Where the equations, kind of like the equations of motion here. It's the same idea. Let's grab this one, this the O2 equations of motion. I thought there should be a way to just download it, but let's grab this. And in the tutorials, oh, not MD, we want the JL. I can grab this and come back here. And I'll say run that notebook code. One, two, three. Oh wait, go MD 1, 2, 3. Spring mass harmonic oscillator. So ddot of x equals negative k, a negative frac of k over m x, and oh, I meant to do this, k m. There we go. So here k is 100, m is 1, so omega, our natural frequency, is this. Then we'll use that same thing, the ordinary differential equations and plots, to actually take a look at what's going on. I could combine some of these with a begin and end. So DDU is this. So this is kind of, this is where I was getting a little, so this is a little different than what I'm used to for defining like differential equations. What I usually think of is like one state variable, but this one is saying that there's like two states, like the x and v, and then we're calculating acceleration. Yeah, and then it gives it an x and a v here. It's not wrong, it's just a little different than what I'm used to. And I was grabbing this from some examples in the Julia documentation, but we can stick with this. So we can integrate it, we can get these values. Oh, and this one is a little bit different, like an ODE.solve. So create that. Oh, so that's what it's doing. ODE.second order ODE problem. So it's expecting second order differential equation where u double prime is f of u prime, u, p, and t. Or p is like the parameters, like omega, and then the time, like what time it is. Okay, that works. Then when we solve it, we get times, we get values, so it's starting off at 2 meters, and then dropping, starting off 0 meters per second, dropping. And we get these curves. So if we say T-span, let's see, T-span is 2 periods of oscillation, 4 pi over omega, and sure enough, that's what we get. And we don't need this one anymore. Let's delete that. And here it's showing me both x and v, like position and velocity, versus like analytical solution of that position. And yeah, do I want to keep adding to it? I feel like I just want to do a dot t SOL of 1, colon. Since we're just kind of looking at the positions anyway. Oh, interesting. What did I mess up? So x0 is 2, v0 is 0. And it should update, right? Yeah, it's weird that, because this looks more like the velocity in here. IDXs. Oh, it's flipping. Oh my god. Okay. Value 2 is the initial position. Value 1 is initial velocity. Weird. Because I'm saying v and then x in here for this second order problem. Yeah, it's just flipping, it's changing the order of everything. All right. And now, if we add this, now I can see sure enough, all of these sine and cosine values, sorry, all of this like sine plus cosine terms, they're exactly in the same spot. If it doesn't look like as smooth as you would think, it's just where it's evaluated. It's not that this cosine curve is actually flat right here. It's just we could add more if we call it like is range, I think range, Lin range, is that right? Like that. 0 to 4 times np dot, or 4 times pi over omega. Let's just wrap it with beginning and end. Lin range. Oh, and then we need what? Oh yeah, it would help if I actually use these evaluate, like the actual thing that I had said I was going to use. And right now I just keep replotting it. So really I don't want to keep adding it to that plot. And there's better ways to do it. But now you can see nice smooth curve and kind of coming in here. And if I want to look at the velocity here, that one's my velocity curve. Cool. All right. So now, one of the things that is a little different about the Lagrange, so here, let's say MD Lagrange definition. It's a principle of least action, right? Where L is T minus V, and int from T1 to T2 of T dt let's say min, something like that. Oh yeah, doesn't like this min. What's wrong with that? Maybe I need some. There we go. Let's call it Q. So the idea, similar to that Brachistochrone problem, but there it was kind of a fabricated thing. Like a ball will roll down any slope, and whether or not it's the fastest slope doesn't, it's kind of cool. Like it's cool that we can figure out what the fastest slope is to maximize like velocity along the whole curve. but it's not like a natural phenomenon. The thing that's weird about this principle of least action is that we're saying the function that happens in a natural kind of system is determined by the fact that it's minimizing this definition of action. So in this case, our let's say we'll give it a begin. T is 1/2 times m times, let's see, what is, so this would be sol 1, right? Let's just define that. V is SOL 1 colon, X is SOL 2 colon, and I think I'm doing this right. And we'll do a dot star. Our potential energy is still a 1/2 times K X squared. And you know what, let's just plot those two. Do I have, yeah, I have T defined, so let's plot potential kinetic energy and plot the potential energy just to see what we've got and what's wrong. Plots dot plot. And I can make this curve a little smoother, but yeah, why am I, oh yeah, it would help if I do this. So there's my kinetic energy and my potential energy. And let's go do that. Since these curves are a little ragged to begin with, let's come back up here and give it a ABS TOL. I think it's, so ODE.solve. Yeah, ABS TOL. Let's make it smaller. I don't know what the default is. It's not really changing. Reltol? There we go. Relative tolerance, make it smaller. Now we have more data points. Looks better. That one, it's probably not changing the, it didn't really change the answer much, but it is giving us like a little more data along there. And what happens when we do this one? And then coming back down here and running this one. Now we have a little smoother curve for that label KE and P. What? Why? Oh, sometimes you have to use these. Yeah, okay. So it likes the double quotes rather than the single quotes. So I've got those, which means that I could also define L is T minus V. And we'll call it the action since it's T minus V. L is action. Oh, like that. And here, it's this different curve. If I add the two, like total energy has to be 0. Or I mean, total energy has to be constant. But T minus V, we're trying to minimize area under this curve in our definition. So let's try to do that. So we'll say we say function right? Function, yeah. And let's give it values of L and values of time. And then we're going to create the total, or at least all the DLs, DL DTs equal 2 through the end minus 1 through the end minus 1. So I'm just taking like all the little differences, and then we'll multiply that by all the little time differences. Right? Because I want to create a sum of all these little, so if I have here going, just creating what is the area like under this curve, and I want to try to minimize that. So I think I'm doing this right. Could be wrong, but just taking a numerical integral, just what is sum, or do I want to take the actual values? Yeah, I don't want to take the differences, right? I want to take the actual value, so this negative 200 times that time step, and then this negative 100 times that time step. Yeah, that makes more sense, rather than the difference. I'm just mixing up my derivatives and integrals, which happens. So the LDTs, all the total LDTs, and then we'll return the sum of LDT. So I get a total of negative 0.6. And it's kind of like, okay, well, so what? Well, let's try it out with the actual analytical functions that we have. So we have velocity is this one. The analytical is that. Am I missing? Yep. X analytical is, I'm just going to grab it from up above. I know I have it in here somewhere. Here we go. Is this one. And then let's grab this stuff. really what I could do is just make a function that calculates this for me based on v and x. That'd be a little better, but leave that. Since I'm doing it more than one time. Oh man, I don't have the multiple cursor. Oh, wrap it all in begin and end. And now integrate action of L analytical and T. Negative 0.58803, and then we get a little bit of difference over here. Part of that is probably some numerical error that's stacking up, but it's kind of weird. But like there could be another function, like maybe it starts at 2 and it's a parabola to get back up to 2, something like that. Like you could make other functions that would satisfy this initial condition and this initial velocity, or maybe not a parabola, but you could make like higher order functions that fit this. So what would be worth trying, same as this brachistochrone, is see if other functions create bigger action. Like, is this the actual minimum action that we can have? It's negative 0.6, and here it's a difference in joules, right? Like or joule seconds, because it's it's joules times delta t. So this is a joule second. 0.6 joule seconds is the minimum amount of action that we can have here. And it's kind of weird, at least to me, this is kind of weird that it actually works this way, and we see this in nature. Like if there's no friction, then it just kind of bounces up and down. It keeps oscillating between maximum potential energy maximum kinetic and maximum potential energy, just back and forth twice per period. So it goes fast, goes slow, goes fast, goes slow. And we see this with pendulums in the same way, but all these oscillating things, they actually follow this, and these natural frequencies and changes in kinetic and potential energy, it's real. So what I'll kind of formalize this and send out like our first idea, but what we want to do is try creating your own functions of things, of like, this is what I think the spring mass would do, and what you'll find is that you're not going to get better than the actual analytical solution, like the solution to that differential equation. You'll always end up with some bigger number for that total action as you integrate it over time, which is kind of cool and spooky, or I don't know. It's up to you, however you interpret that. Cool. So that's kind of wrapping up that brachistochrone, like trying to show some numerical integration stuff, and like using Pluto to like get some insights into these different kinds of problems.